So in this presentation, we'll take a look at how to integrate ground source heat pump systems into the building design. We'll consider energy demand profiles important for ground source heat pump systems, as we cannot design on capacity alone. Part load conditions also an important aspect. What kind of ground source heat pump system types can we distinguish? Emission systems, integration of heat pump energy central and the building, and we'll take a look at some opportunities for optimization. Now, an energy demand calculation, a typical procedure without considering domestic hot water, is based on the heat loss and cool loss. Usually, the heat loss or cool loss are calculated at fairly extreme conditions in the Netherlands, for instance, at -10 degrees outside temperature and 7 meters per second wind speed. So a fairly extreme design day to give us a maximum capacity required by the building. Based on this calculation, we then select the capacity of the generating system, the boiler or the chiller, and we have a little bit of over-design, like 20 or 30%, so the users will always be comfortable. For a ground source heat pump system, this approach does not work, and it will result in a very costly over-design. Of course, very often you do not need maximum capacity. Not only for only a few days of the year will it be very cold, but in fact, the extreme conditions only occur once every 5, 10, 20 years. So we need to have a more accurate estimate of the energy demand, because the energy is much more important than the capacity. The energy is what we take out from the ground and which will cool the ground down in heating, and we put it back into the ground. It will heat the ground up during cooling. So this energy balance on the ground side is very important for the design of the system. And if we don't have that correctly calculated, we get a very costly over-design. This is due to this thermal memory of the ground. There are a few recommended procedures. One recommended procedure is, if we only have a heat loss and cooling loss calculation, to have a reference climatic year. The graph on the right shows the ambient temperature in the Netherlands for the reference climate year. And then we have like a heating curve and a cooling curve where we say, well, at this ambient temperature, -10 degrees, we'll have this 8.5 kilowatt capacity requirement, but at -5 we only need 6.5 kilowatts, and at 5 degrees we mainly only need 2.5 kilowatts. So by taking a look at the ambient temperature for every hour of the year, matching it with the capacity requirement for that particular temperature, we can calculate the total energy demand over the complete year, taking into account part load conditions. If we do this for different climates with 8.5 kilowatts heat load and 3.5 kilowatt cooling load, we can see a huge difference between the heating demand and cooling demand for climates in Helsinki, Strasbourg, or Athens, which are in fact the northern reference climate, the middle European reference climate, and the southern European reference climate for the norm EN 14825, which is the norm to calculate seasonal performance factor at part load conditions. Keep in mind that this is still a reference year, and of course this reference year is still fairly conservative. Another method, recommended procedure number 2, is to do an actual dynamic building simulation. So we've got a complete physical model of the building, and we have again a reference year or a climatic year that we use to calculate the heat demand curve and the cool demand curve over the year, and then we can graph it in the way that is shown on the bottom left. How many hours of a high capacity are required for heating, and going to the right we see that fewer and fewer hours are required, or more and more total hours are required for the total heating demand. In fact, if we look at the part load conditions, we can see that with a smaller capacity, we can already do 80% of the heating load, 12.0 megawatt hours, and an even smaller capacity will allow us to do around 70% of the total heating demand.